This week we're continuing our look at numerical calculus, but focusing this lecture on numerical differentiation as opposed to last lecture where we focused on numerical integration. To begin looking at numerical differentiation, we're going to start all the way back at what the definition of a derivative was. So if you remember back to your first calculus class, early on, the first, maybe the second week, you looked at what is the definition of a derivative, or how do we find the slope of a line at any point along the line. So we defined our derivative as, let's say, dy dx for some function y, which we could also call y prime. But the limit definition of this, that we later had shortcuts for, but early on we said the limit as h goes to 0 of y of x plus h minus y of x over h. So basically what we were looking at here was the rise over the run in order to come up with what the slope was. As the picture indicates, if we find these 2 points on our line, f of x or y of x, and f of x plus h or y of x plus h, if we find the difference in their height, that is going to be the rise, and then the difference between x plus h and x is just h, and that's their run. So by finding this ratio, we came up with what our derivative was. And we saw that as h gets smaller and smaller, meaning that we're taking these points infinitely close together, we're going to find exactly what the derivative is, or exactly what the slope of the line is at that point. When we were solving this by hand, what we could do is let h go to 0, and we could, by hand, calculate what the limit was, and that would give us our derivative. Or later on, we could use power rule, chain rule, things like that. But for all the problems, we could let h go to 0 and use our limit rules to get the derivative that way. Unfortunately, the computer doesn't know limit rules, at least the way that we're going to be programming it here. So we can't actually let h go to 0, because we see what happens is the denominator is going to go to 0, which means it's going to be some number over infinity. But the basic premise of what we can do is if we make h very, very small, not equal to 0, but relatively close to 0, we can get a pretty good estimate as to what the derivative of our function is. And furthermore, we can calculate the derivative at every point in our function. By allowing the value of x to change, and the way we're going to look at making our h value constant, we can march along changing the value of x and find the derivative at every point. We're going to use what's called finite difference methods in order to calculate the derivative, and there's 3 basic kinds we're going to look at, and sometimes use all of them together. So the most basic way is forward differentiation. So here I'm changing up the notation a little bit here because we're talking about discrete points, not a continuous function. So we might have 100 points of data, so xn is the nth point of data that I'm talking about. So for example, if I have 100 points, I'm looking at the 20th point, that would be x sub 20, where n is 20. So if I want to know the slope at the 20th point of data I have, then using forward differentiation, what I can do is find the function's value at the 21st point minus the function's value at the 20th point. That's the y of n plus 1 minus y of n. So again, here n is 20. I want the derivative at the 20th point of interest. And I can divide that by my independent variable at the 21st point minus my independent variable at the 20th point. So again, all I'm doing here is taking the rise over the run in this very simple definition of using forward differentiation. One thing to note here, that again, if I'm talking about the nth point, I'm going to use the n plus first point, so the next point in the sequence, and the nth point to calculate the forward derivative. Alternatively, I can use the backward derivative, and these are not going to give me necessarily the same answer. In fact, they're probably not going to give me the same answer. So let's look at the difference here. If I want, again, the derivative at the 20th point, I now take for my numerator the value of my function evaluated at the 20th point minus the function at the 19th point. So I'm actually using the point before the one of interest, in contrast to forward differentiation, where I use the point of interest and the point after it. In backward, I'm using my point and the one before it. And the same for my independent values. I'm taking the 20th value of x minus the 19th value of x to calculate the backward difference. I can also find the central difference. So again, in this example, if I am interested in finding the derivative at the 20th point of x of my function, I actually take my function at the 21st point minus the function at the 19th point, over the independent variable at the 21st minus the independent variable at the 20th. In this case, at least for the first order central differentiation, I don't actually use that point of interest, in this case 20. I use the one after it and the one before it. So again, to recap, there's these three basic methods we're going to use: forward, backward, and central. Each one has its particular use, and we'll see what some of the differences are in a second here. Right, so with the forward differentiation, kind of the most basic type, one drawback of using our forward differentiation is that we cannot use it in real time. And the reason for this is, if we have our clock going and we're collecting our data, if we want to know the derivative right now, since we don't have any data beyond right now, we can't use the forward differentiation, because again, that relies on, to know the derivative at some point, I need to know the value of the function at the following point, which in real time we wouldn't know. So that's one drawback of using a forward differentiation. In contrast, backward differentiation can be done in real time, because again, referring back to those equations we just looked at, in order to conduct the backward difference, if I want to know the derivative at a point in time, then I need to know its functional value at that point of time and the function value at the previous point in time. So in real time, we can use backward differentiation since we know everything that happened before our current state in time. And with the central differentiation, what we're going to see in the following slides is that central differentiation is actually more accurate than forward or backward differentiation for the same amount of data that we had. But fortunately, because the central differentiation needs to know points in the future of the point that we want to know the derivative of, we cannot use central differentiation in real time, just the same as we can't use forward differentiation in real time. So even though we have these three kind of distinct methods for doing it, based on a set of data, we might use all three in order to calculate what our derivative is at all points in time.